Let's solve problem number 7 on recurrences using substitution method. Here is the problem. Consider the recurrence function. We have this recurrence function Tn equal to 2t square root of n plus 1 if n is greater than 2. If n is less than or equal to 2 and if it is the case n is greater than 0, then Tn must be equal to 2. This is the base case, Tn equal to 2, and this is the recursive case. We are well aware about the recurrence relation and what they represent. They represent a recursive function. We can call this a recurrence function, or we can say this is the recurrence relation. We are available with this recurrence relation. Then Tn in terms of theta notation is it option A, theta of log n? Is it option B, theta of log n? Is it C, theta of square root of n? Or is it D, theta of n? This question has been asked in GATE 2017. We are told to find the value of Tn in terms of theta notation. This means we need to find the asymptotic value. We need to represent Tn in terms of theta notation. In order to do this, we need to solve this recurrence relation. We can solve this recurrence relation using the substitution method. So now let's try to do this. Let's apply the substitution method to this recurrence relation and let's try to solve this. In order to solve this recurrence relation, we need to provide some space here for the solution. So now let's remove this part of the problem and let's solve this problem. Here we have Tn equal to 2t square root of n plus 1. This is the recursive case. This is true if n is greater than 2. If n is less than or equal to 2, and if n is greater than 0, then Tn must be equal to 2. This is the base case. We know how to use the substitution method to solve these type of recurrence relations. We need to start from the recursive case and we need to gradually move towards the base case. Let's do this now. Let's apply the substitution method to this recurrence function, or we can say recurrence relation. According to the substitution method, we need to take the recursive case first. So let's take Tn equal to 2t square root of n plus 1. This is the recursive case. Now, we can substitute t square root of n by 2 times t square root of n plus 1. Why? We can always replace n by square root of n. In the left hand side, we will get t square root of n. And in the right hand side, we will get 2 times t square root of n plus 1. So this means we can replace t square root of n by 2 times t square root of n plus 1. After replacing, or we can say substituting t square root of n, we will get this equation. Tn equal to 2 times tn power 1 by 2 square plus 1 plus 1. I have used these square brackets to indicate that this expression represents t square root of n. Here we have 2 times tn power 1 by 2 square. Now you might be thinking why I have written n power 1 by 2 square here in place of square root of n. Think about it. What is the meaning of square root? We know if we have square root of n, this means it is equivalent to n power 1 by 2. And if we are taking square root of n, this is equivalent to n power 1 by 2 square. We are multiplying 1 by 2 by 1 by 2 in the power. That's what we are doing here. So this is the reason why we are getting n power 1 by 2 square. Now we can expand the brackets. We now need to multiply 2 by 2. We will get 2 square here. This is 2 square times tn power 1 by 2 square. And here 1 is also going to multiply by 2. We will get 2 here. So the equation so obtained is Tn equal to 2 square Tn power 1 by 2 square plus 2 plus 1. This is according to the substitution method. Now we have this new Tn in terms of Tn power 1 by 2 square. We can proceed further and replace or substitute Tn power 1 by 2 square by 2 times Tn power 1 by 2 cube plus 1. We just need to replace n by n power 1 by 2 square here. So we can replace or substitute Tn power 1 by 2 square by 2 times Tn power 1 by 2 cube plus 1. The rest of the equation remains as it is. Now, in the same way, we can multiply 2 square by 2. We will get 2 cube here. This is 2 cube times Tn power 1 by 2 cube plus 2 square, because 1 is going to multiply by 2 square. We will get 2 square here, then plus 2 plus 1. This is the equation so obtained. Now here we can observe a pattern. In this way, we can continue forever. Let's say we continued up to Tn power 1 by 2 power k. Let us assume we have reached the base case if we reach Tn power 1 by 2 power k. We can observe a pattern here. When we have n power 1 by 2 power 3, this means if we have 3 as the power of 1 by 2, then here also we have 3 as the power of 2. Then we have 2 power 2, 2 power 1, 2 power 0. The powers are decrementing by 1 every time of 2. Same thing we can observe here as well. If we have the power as 2 of 1 by 2 here, then here also the power must be 2 of 2. Then we have 2 power 1 here, then 2 power 0. In the same way, we can say if we continue up to Tn power 1 by 2 power k, then the equation must look like this. Tn equal to 2 power k times Tn power 1 by 2 power k plus 2 power k minus 1 plus 2 power k minus 2 and so on up to 2 power 1 plus 2 power 0. 2 power 0 is equal to 1, that's why I have written 1 here. We are getting this from this pattern only. Here we can observe we have n power 1 by 2 power 3. Here we have n power 1 by 2 power k. In place of 3, now we have k here. If we have 3 here, then we must also have 3 here. Similarly, if we have k here, then we must also have k here. That's why I have written 2 power k here. And why I have written 2 power k minus 1 here? Because we can observe in this pattern that if we have 2 power 3 here, then we must have 2 power 2 here, then we must have 2 power 1 and then 2 power 0. This is the reason why I have written 2 power k minus 1, then 2 power k minus 2, then 2 power k minus 3 and so on up to 2 power 1, 2 power 0. This is Tn in terms of Tn power 1 by 2 power k. Now let us assume Tn power 1 by 2 power k is the base case. Here we can observe that in place of n we have n power 1 by 2 power k, and the base case is when Tn is equal to 2, if n is less than or equal to 2 and n is greater than 0. Let us assume n is equal to 2. This means n power 1 by 2 power k is equal to 2. This is my assumption. I am assuming this is the base case. As I want to end the recursive procedure, that's why I am assuming this. So it is my assumption that n power 1 by 2 power k is equal to 2. If it is the case, then the base case is reached. Now we need to find k in terms of n so that we can replace k here by n. Eventually, we are interested in finding the asymptotic value in terms of theta notation, and that too in terms of n. So it is important to replace k in terms of n. Let's do this now. We can bring k down by first taking log on both sides. So let's apply log on both sides. After applying log on both sides of this equation, we will get log n power 1 by 2 power k base 2 equal to log 2 base 2. I have chosen the base as 2 because the constant here is 2. If I take base as 2, we will get 1 here. It is better to get 1 here in the right hand side so as to simplify the calculations. Now we have log 2 base 2 in the right hand side. We can rewrite this as 1 because log 2 base 2 is 1. Now what about the LHS? Here we have log n base 2 power 1 by 2 power k. We can apply the property of logarithm here. Log a power b base c is same as b times log a base c. So 1 by 2 power k will come in front of log n base 2. So we are getting 1 by 2 power k times log n base 2, and this is equal to 1. Now we can multiply 2 power k on both sides. After multiplying 2 power k on both sides, we will get log n base 2 in the left hand side, and in the right hand side we will get 2 power k. So we are getting log n base 2 equal to 2 power k. Now again we can apply logarithm on both sides because our final goal is to obtain the value of k in terms of n. So we need to bring k down, and how can we bring k from power to the base? By applying log on both sides. As simple as that. So let's do this. Let's apply log on both sides. After applying log on both sides, we will get log base 2 log n base 2 equal to k. Log 2 power k base 2 is same as k times log 2 base 2. By applying the same property we have applied here, we know log 2 base 2 is 1, so we will get k here. Reason why I have chosen the base as 2 is because this 2 will be removed and we will be left with k only. Now we can observe that we have k equal to log base 2 log n base 2. Now, instead of replacing k by log base 2 log n base 2 at this moment, first we will try to solve or minimize this equation. Here we have 2 power k times Tn power 1 by 2 power k. First thing we can do here is we can replace n power 1 by 2 power k by 2. This is what we have assumed. So we will get T2 here. And what is the value of T2? We know if n is equal to 2, then T2 is equal to 2. So we can replace Tn power 1 by 2 power k by 2. We know n power 1 by 2 power k is 2 and T2 is equal to 2. Here we are getting 2 power k plus 1 because 2 power k times 2 is 2 power k plus 1. We can observe this is the equation we have here. 2 power k plus 1 plus 2 power k minus 1 plus 2 power k minus 2 and so on up to 2 power 1 plus 2 power 0. Now, let's forget about this term for a while. Let's focus on the remaining part of the right hand side. Here we have 2 power k minus 1 plus 2 power k minus 2 and so on up to 2 power 1 plus 2 power 0. We can observe this is forming the GP series. How? We know what GP is, geometric progression. If we start this series from here, the first term is 2 power 0 which is equal to 1. And here each term is obtained after multiplying the previous term by 2. This means the common ratio is 2. We can observe this term is obtained after multiplying this term by 2. Similarly, the next term after this will be 2 square, and 2 square is obtained after multiplying the previous term 2 by 2. So clearly the common ratio is 2, and we can observe the first term is 1. We know the sum of GP series is a times r power n minus 1 divided by r minus 1. As the common ratio is not less than 1, it is greater than 1. Therefore, the sum of the GP series is a times r power n minus 1 divided by r minus 1. As I have mentioned this earlier as well, if the common ratio r is greater than 1, then the sum of the GP series is a times r power n minus 1 divided by r minus 1. If it is the case that the common ratio is less than 1, then in that case, we will have the sum of GP series as a times 1 minus r power n divided by 1 minus r. In this case, the common ratio is 2, which is greater than 1. That is why the sum of GP series is A times R power n minus 1 divided by R minus 1, where A is the first term, R is the common ratio, and n represents the number of terms in this GP series. We can observe from 2 power 0 to 2 power k minus 1, we have a total of k terms. This one thing is clear. So n is equal to k. What about R? R is equal to 2. What about A? A is the first term and we know first term is 1. So we know A, R and N. We can use the formula of the sum of GP. We can now replace this sum by 1 times 2 power k minus 1 divided by 2 minus 1. We can observe 2 minus 1 in the denominator is equal to 1. So we will be left with only the numerator, which is 2 power k minus 1. Now we have the simplified form of this equation. Tn is equal to 2 power k plus 1 plus 2 power k minus 1. Now we can replace k by log base 2 log n base 2. Let's do this. After replacing k by log base 2 log n base 2, we are getting this expression. 2 power log base 2 log n base 2 plus 1 plus 2 power log base 2 log n base 2 minus 1. Now we can take 2 power log base 2 log n base 2 common from these two. We will get 2 power log base 2 log n base 2 times 2 plus 1 minus 1. And what is 2 plus 1 minus 1? 1 minus 1 is 0. We'll be left with 2 only. This is 2 power log base 2 log n base 2 times 2. Now we can apply the property of logarithm. A power log b base 2 is same as b power log a base 2. So we can bring this log n base 2 to the bottom. We will get log n base 2 to the power log 2 base 2. We know what is log 2 base 2. Log 2 base 2 is equal to 1. And therefore, we will be left with log n base 2 times 2. We can rewrite this as 2 times log n base 2. But at the end, the asymptotic complexity will be theta of log n. Why are we getting theta of log n here? The reason is simple. We can eliminate the constant and the base and we will be left with log n only. This represents the asymptotic complexity of Tn. So Tn is theta of log n. So Tn is asymptotically equal to log n. This is what we can say. And therefore, we can say option B is the correct option. I hope it is clear how to solve these type of problems. So with this, we are done with the problem. Okay friends, this is it for now. Thank you for watching this presentation. I will see you in the next one.